please support me through PayPal to devinwyndham@gmail.com. Alright, in this video, I want to talk about understanding complex numbers. Let me give an introduction to this. So, I think I'm good at math. The reason I think I'm good at math is that I understand math, but that wasn't always the case. I used to try to memorize my way through math, and that didn't really work for me. And I think it will help you also if you try to understand math as much as you can. So, in the educational system, I think worldwide, teachers try to help us understand, but there are some things where that system breaks down, I guess, because there's so much to teach us. The first case I can maybe think of as where that breaks down is the area of a circle. They just tell you the area of a circle is pi r squared without proving that. I think that proof should be done because I think high school students could prove that the area of a circle is pi r squared, and so I'm trying to revolutionize worldwide math education. Another area where I think understanding breaks down is complex numbers. You may have studied complex numbers. They're like imaginary numbers with basically it's the number I. So basically we're understanding the number I. Teachers frequently just say, well, just pretend I is a real number, so that all the properties we've learned for real numbers, like the distributive law, the associative law, and the commutative law, will just continue to hold when we work with I. The problem, though, I see there is that I is not real. So how can we just take for granted that those properties work? Think math is a lot more fun when you understand things. So this video is going to try to help us understand complex numbers. All right. So let's start with a bit of history. In the 1500s in Italy, people were trying to, I'm simplifying here, but they were basically trying to solve this equation, x squared equals -1. All right, maybe put the video on pause and try to solve this equation. All right, you might think, well, let's try -1. Well, look what happens. If you do -1 squared, you got 1. And if you think about this, there is no solution in the real numbers to this equation. So what people did is they just said, okay, well, we'll just expand that. We'll just invent a number. We'll call it I. I is an imaginary number. I don't think they chose I. I'm not sure. I'm not sure if I is chosen because it's the first letter of imaginary, but it works out well. So that's just a way to remember it. I is the first letter of imaginary. I is an imaginary number because it sort of doesn't exist. But people just made it up to solve this equation. So we're going to define I so that I squared equals -1. And this is what I mean. Like if we have this I floating around, how can we all of a sudden just welcome it to our family of real numbers and say it can play nicely with our real numbers with all the properties that we know, like the associative law, the commutative law, and the distributive law that we know and sort of understand for real. So again, what this series of videos is going to try to do is help us understand complex numbers. To that end, I'm sort of spoiling the end of this mystery. I said, like, what high school teachers tell you is to just pretend I is real, and that's basically because it works. We can just pretend that I is real, but I want to know why, and I hope you want to know why too. Why can we just pretend that I is real? And so to see that, let's make a list of the properties of real numbers, and then try to transfer those properties to when we get I in there, complex numbers. All right, so let's go back and just think about a real number. So we have properties of real numbers. 1, the real number system is a set with an operation plus. So a real number is any number that can be represented on the real number line, and an operation for our purposes, is going to take two elements of that set of the real numbers and return an answer in that system of real numbers. So the real number system is a set with an operation plus. Property 2, plus is commutative. That basically means that the order when you add things doesn't matter. Negative 8 plus 13 is 13 plus negative 8. They're both equal to 5. Let's talk about the etymology of this word. So this comes from Latin. Mutare means to change. Can you think of other words that have to do with change and this Latin mutare? Well, there's commute. You commute to work, like you're changing your location. Com comes from Latin cum, which means with. It's also an intensifier. It strengthens things. So it just means, I guess, changing very much or something. So there's commute related to this. We're changing the order. Mutation in biology, it's like a change in genes or something like that. So anyway, that is the commutative law. Plus is associative. That means like you can group things in either of these two ways. You know, if these are just examples, but you know, we could do this with any three real numbers. So, for example, negative 7 plus 6 plus negative 21 is equal to negative 7 plus 6 plus negative 21 with these groupings implied by these brackets. All right, this is an interesting symbol. This double arrow means it's equivalent to. Let's actually, and I use this a lot in my proofs, so let's talk about what equivalent to means. This equivalent symbol connects two statements that are either both true or both false. So let's pretend we don't know if this is true or false at the beginning, but we're going to connect it with a statement that's going to have the same truth value. Because what I do is I can simplify in here. I know that, you know, this is negative 1, and this is negative 15. So these two statements have the same truth value, and we'll keep going. So this is negative 22, this is negative 22, so this statement and this statement have the same truth value. Now, this is obviously true, so we can work backwards. Since these three statements have the same truth value, and this is true, the original statement is also true. So we've basically proven this for these numbers at hand. That's the associative law. All right, there exists an additive identity. That is, there exists a real number e. Now, I don't mean the e that's about 2.71. I'm just choosing e for like the identity here. There exists, well, I said the identity. Maybe I should have said an identity. There exists a real number e such that for all, this upside down a means for all, such that for all reals, e plus a equals a plus e. All right, pause the video and tell me if you can think about what real number could be an identity. All right, 0. The additive identity is 0 because, you know, it satisfies this property. And it is unique. What does unique mean? Unique comes from the Latin unus, unus, which means one. In the Bible, it says Jesus is the unique Son of God. That means he's the one and only one Son of God. If you say that shirt is unique, it means that shirt's really cool because there's only one of that shirt in like the whole wide world. So unique means one and only one. So we're saying that there's no other number besides 0 that satisfies this property. So there's a one and only one additive identity for the real number system. All right, 5. For all reals, there exists, for all a in the reals, there exists b in the reals. This backwards e means there exists, such that a plus b equals 0. So what we're establishing here is called the additive inverse. Basically, we can get back to our additive identity. So for instance, if we start with 7, we can get, I shouldn't say get back, we can get to the additive identity. We can get to the additive identity by adding its inverse. Right, so I think it should be obvious to you that every number has an inverse. It should also be obvious to you that, you know, for any real number, its inverse is unique. Its additive inverse is unique. There's only one. All right, so those are some properties for adding real numbers. I think this is a good point to end this first video on understanding complex numbers. Please subscribe to my channel.